In this lesson, we're going to be adding another tool to our integration toolbox. It is called integration by parts. And it's special for us because the first 4 strategies that we have in our toolbox already are learned by AB and BC students, but by parts is only learned by BC students. So it's our first exclusive BC topic. Our learning target says to find antiderivatives using integration by parts. And just know going into it that integration by parts basically reverses the product rule when we take that antiderivative. Before we learn how to use our strategy of integration by parts, we need to know when to use it and why we use it. And to contrast it to what we were working on the past 2 lessons, substitution, we were finding a u function and a du function, which was the derivative of u. And so we were looking for 2 functions that were related by a derivative. Often they were a composition of functions, and sometimes they were a product. So by parts is different because it is a product, but it's of a function u and another function we'll call dv. And we're using v instead of the u because we want to show that these 2 functions are unrelated to each other through a derivative. So now we'll look at the product rule and see how that is going to help us derive the formula that we're going to use with integration by parts. So let's start with the product rule. We're going to take the derivative of the product of 2 functions, u and v. When we do that, we've learned left d right plus right d left. So in the context of u times v, we get the left function u times the derivative dv plus the right function v times the derivative du. And now what we're actually going to do is take that equation, and on both sides we'd like to integrate or take the antiderivative. What happens on the left side, as you know, when we take the integral of a derivative expression, those 2 functions are inverses, or inverse operations, so they cancel each other, and we're left with just u times v. And on the right side, I've used one of our properties of integrals, which says if we have a sum in our integral, we can split it up into the sum of 2 separate integrals. And if you remember, when we started the conversation about integration by parts, we said we were going to try to integrate the product of u and dv. So you'll see that we have the integral of u dv here. So what I've done to start solving for that expression is to subtract the integral of v du from both sides of the equation. So we have the uv subtract the integral of v du is equal to the integral that we want, which is the integral of u dv. So finally, just by switching that equation around or flipping the 2 sides of the equation, we get our formula for integration by parts, which is the integral of u times dv equals uv minus the integral of v times du. And you have to be careful, especially somebody like me with not the neatest handwriting, that your u's and v's definitely look different. They are very similar letters, so just be careful with that. And also, this is not the easiest formula to remember. So when I learned calculus a long time ago, my teacher gave us a little memory trick. So this formula is ultraviolet voodoo. And I think that's probably the best thing you can come up with to remember how those letters go. And just remember that the second voodoo has the integral in front of it. So let's take a look at our first example. And while we're talking about the example, we're going to also talk about these steps that we'll take in order to work our way through the process of integration by parts and using the formula for integration by parts. So the first 2 steps happen almost at the same time. We're going to define which function that we see in the integral that we would like to be the u function and which function we'd like to be the dv function. Then we're going to find the du, the derivative of u, and we're going to find the v, which is the antiderivative of dv. So we want to make our choice based on which function we choose for u should be something we can easily take the derivative of, and the function that we choose to be dv is something we can easily take the antiderivative of. And that's relatively speaking, and there's not always a right choice, but a lot of times there's a more efficient choice. So if I look here at our first example, I have x and I have cosine of x. Let's suppose that I let u be cosine of x and dv be x. That means I'd have to take the antiderivative of x, which would introduce an x squared over 2, and the derivative of cosine would introduce a negative sign. That's probably not my most efficient choice, so let's try it the other way around. Let's let x be our u function and cosine of x be our dv function, so that when I take my du, I simply get 1 dx. And when I take my antiderivative of dv, I get a positive sine x. So I hope you can see that that's the better choice than introducing both a negative and a fraction. So now that we've made those first two important decisions and we've got basically our setup, it's kind of our side work, I like to put it in a box, we are going to jump right to step 3, which says substitute into the formula that we just learned. And remember that our x was u and our cosine x was dv. So we've just got to come up with an expression for uv minus the integral of v du. So I thought using these arrows right from the formula might help us see that we're just going to pull these values from our setup that we already figured out. So u times v ends up being x times sine x minus the integral of v times du, which is the sine x times dx. So now that we've gotten our formula set up, that's great, but as you can see, we still have a little more work to do because we have an integral that we can simplify. So the first term, the x sine x, simply gets brought down. It stays in the front of our answer. When I take the antiderivative of sine x dx, I get a negative cosine, so just be careful there with the minus from the formula. It does create a plus cosine x, and since there are no limits to deal with, I have to remember my general constant plus c. So that expression is our final answer to the integral of x cosine x dx. And what I want to show you now is an alternative method that's called tabular integration. It's a really neat method. I wish I could tell you which mathematician I could credit it with, but when you see it, I think it's pretty amazing the way it's set up and the way it gives us our perfect right answer. But I want to caution you that we can only use it when the derivatives of u eventually go to 0. So something like x, where we got the derivative, would be 1, the next derivative would be 0. So basically any polynomial that you choose for u is going to eventually derive down to 0. So this is a perfect example. I'd like to show you how to use tabular integration and end up with the same answer. As you can see, it's a 3-column chart. We're going to have a column for u and its derivatives, and we've basically already started that chart and talked through it. We started with u as x. The first derivative of that would be 1, the next derivative would be 0. And so basically that column ends when you get to 0. The second column starts with dv. You take the antiderivative, which you've already thought about in that example, is sine x. And we're going to need to take one more antiderivative, which is negative cosine x, because you're going to see in a minute that we're actually going to draw diagonals to connect these 3 columns. So we'll need one more row in our second column than we do in our u column because we need the 1 to multiply that. We'll see that in a second. The third column is you're just putting signs, positive, negative, you're alternating, and you always start with positive to make this combination work. So believe it or not, once we have our columns set up, it's actually going to give us diagonals that when we take the product of the diagonals, we get the exact correct answer. So let me show you what I mean. The first column, we have an x times diagonally a sine x times diagonally a positive sine. So that gives me a positive x sine x. Starting in our second row, we have a 1 diagonally times a negative cosine diagonally times a negative. 2 negatives give me a positive cosine x, and then we get plus c, so we have a perfect match for our answer. So now that you've seen tabular integration, I hope you agree that sometimes that might be a little easier method than thinking through the formula. So when you look at this next example, we have another good opportunity to try the tabular integration because we have this x squared that will eventually derive down to 0 after a few derivatives. So we're going to let dv be the other function, which is e to the negative x. So I'd like you to go ahead and fill in that table for us, the 2 columns, and then try to come up with the final answer. In this next example, it looks like we can use tabular since we have an x squared that would derive to 0. But if we try to put natural log of x in our dv column, we don't have an antiderivative for natural log of x. So we need an efficient system for how we choose our u function. So if we have any of these special functions, they are automatically going to be our u function: inverse trig, natural log, algebraic trig, and exponential.